This video is intended to accompany the Advanced Topics Lesson 3.6 through 3.7, Example 1. In Example 1, it asks you to consider the function f of x and asks you some follow-up questions, the first one being determine the x-intercepts. So as a reminder, an x-intercept is the location or the x value where the y value is 0. So in other words, we want to know where this function would equal 0. In other words, where the output value would be 0. So in order to solve this equation, you would first take the denominator, multiply it over to the left-hand side, and you would end up getting that the numerator is equal to 0. Now, as a reminder, you have 3 factors here, and each of those factors multiplied together is being set equal to 0. And so you can say that you also want to solve where each of the factors equals 0. Well, 2 is never going to equal 0, so that's not going to happen. If x minus 3 equaled 0, then that would mean that x equals 3. And if x plus 2 equaled 0, that would mean that x is negative 2. Now, I would suggest that we take these two numbers and we try plugging them back into the original function to make sure that they work. You'll notice that when you do that, because you have an x minus 3 in both the numerator and the denominator, when you plug in x equals 3 in for the f of x, you're going to get 0 divided by 0, which is undefined. So in this situation, x equals 3 is not an x-intercept because you get an undefined answer when you try to plug it back in. Now, x equals negative 2, if you try to plug that back in, you're going to get 0 divided by some number, which is 0. So this is an x-intercept. And we have one x-intercept for this function. Question B asks us to determine where the y-intercept occurs. As a reminder, the y-intercept occurs when x equals 0. So for the y-intercept, we're trying to find f of 0. So you're going to take 0 and plug it in everywhere you see an x. So we're going to take 2 times 0 minus 3 times 0 plus 2. Divide that by 0 minus 3 times 0 plus 1. So this is 2 times negative 3 times 2. And the denominator is going to give us negative 3 times 1. So if you simplify this, you're going to end up getting 4. So the y-intercept is at 0, 4. Now, question C is going to ask us to find the domain. As a reminder, the domain is all of the x values that work for this function. So we have a rational function in this situation. I'll recopy down f of x for us so that we have it. You'll notice that we have a rational function here, so we need to be concerned about where the denominator would be equal to 0. And the denominator is going to equal 0 at x equals 3 and x equals negative 1. So we have two values that are not going to work. Oops. Two values, positive 3 and negative 1, that are not going to work for this function. So if you were going to write your domain in interval notation, you would go negative infinity to negative 1, union, negative 1 to 3, union, 3 to infinity. So you're going to have two holes in your function. Question D, as in dog, asks us to determine the asymptotes for our function. Let's start with our vertical asymptotes. Vertical asymptotes occur where the denominator could equal 0 and where you have terms that do not cancel from numerator to denominator. So as a reminder, this x minus 3 that you have in the numerator and in the denominator, that ends up basically giving you a hole in your function that is not a vertical asymptote. It's called removable discontinuity. So this situation, you end up getting something like this or something like this, where you have a hole in your function at x equals 3. But the x plus 1 here, the -1 that's occurring there, that is your vertical asymptote. So we have a vertical asymptote at x equals -1. Horizontal asymptotes, as a reminder, there's 3 things that you need to check for horizontal asymptotes, and it has to do with the degree of the numerator and the denominator. In this situation, the degree of the numerator is x, or is 2, because you have if you were to FOIL this whole thing out, you'd get x squared. Same thing down here, you have a degree of 2, because if you FOIL this whole thing out, you'd get an x squared as well. So we have, in the numerator, you would have f of x equals, if you were to distribute, 2x squared plus a bunch of junk over an x squared plus a bunch of junk. So in this situation, they have the same degree in the numerator and the denominator. So the horizontal asymptote is going to occur at the ratio of the leading coefficients. So we're going to get basically 2 over, this is like a 1 in front of this x squared. So you have a horizontal asymptote at y equals 2. Question E says, are f and the function g of x, which is 2 times x plus 2 over x plus 1, are they the same function? So let me get this so we can see both of them at the same time. Here's your f and here's your g, and the question is, are these the same function, why or why not? So basically what we've done is we've canceled those x minus 3's and we've said, okay, are they the same? They are going to be the same everywhere except for at x equals 3. At x equals 3, this function exists. This function does not exist. So g of 3 exists, but f of 3 does not exist. You would get a hole at x equals 3 for f, and for g, you would get a point that is plotted. So in other words, the hole would get filled in for g. So also at the end of question E, it asks you to think about limits. Let's think through those slightly. So limit as x approaches infinity of g of x, and the limit as x approaches negative infinity of g of x. Let's start with infinity. So as x approaches infinity, so as you're going to the right for this function, what is the y value approaching? So this is talking about end behavior. Because we have a horizontal asymptote at y equals 2, as our x's approach infinity, they're going to approach our y value of 2 because of this horizontal asymptote. So this is going to equal 2. As you go to the left, similarly, the exact same thing is going to happen. This is also going to approach 2 because of that horizontal asymptote. Now, if you wanted to test this, you could plug in some very large numbers for x, and you could see that this function is going to approach numbers that are getting closer and closer to 2. Same thing would happen here if you plugged in negative values that were very large. So, you know, negative 55,000 or something crazy like that. This also would approach positive 2. You've got an x over an x, and the negative in the top and the negative in the bottom would make this positive in this situation. Now, just as a side note, I used the horizontal asymptote information from f to talk about g. And the reason that we can do that is because these two functions are the same everywhere except for at x equals 3. X equals 3 is not anywhere close to infinity or negative infinity in this situation. And so we can use f to talk about the limit at infinity for g. In other words, this would be the same as the limit as x approaches infinity for f. And this is the same as the limit as x approaches negative infinity for f.